right, let's go over this homework question. Oh, there's two of them here. Which one? Do you want me to do them both?
I think you just
Even if we start the second one, just so I can, because there's two of them like that.
Okay, let's do it. Okay, first one is on a geometric series. This is number 4, 9.2. Number 4, find the sum of the convergent series. So we have this series starting at 0, going to infinity of 7 times 5/6 to the n. Now, when it's written in this form, you know it's geometric, okay? Because here, let's write out a few terms. When n is 0, you're going to get this 5/6 to the 0 power, which is 1, so you get 7, plus. When it's 1, you're going to get 7 times 5/6. And then when n is 2, you're going to get 7 times 5/6 squared, etc. Okay? This is geometric. Each term is multiplied by 5/6 to get to the next term. Since r is 5/6, okay, that's called a common ratio. That's the number that you multiply each term by to get the next term. Since r has an absolute value less than 1, this converges. It has a sum. Okay? The sum is equal to a over 1 minus r. I would certainly expect you to know that. I would give you a problem like this on the test. Okay? A is 7. R is 5/6. So we get 7. 1 minus 5/6 is 1/6. We get 42.
Is there a reason this is on the floor?
Yeah, just leave it on the floor. Oh, yeah. Oh, yeah. They don't have a box here. Hey, I don't know. Sometimes they have a box in the desk, but sometimes he puts it out there. So, I don't know. Okay, is that reasonable there? That's it, that's the answer. Okay. The next one, it says, consider the following, and they give you a series, and then it says, use a graphing utility to find the indicated partial sum and complete the table. Oh, boy. And then use a graphing utility to graph the first 10 terms of the sequence of partial sums, and a horizontal line representing the sum. And you've got 2 of them on here. Okay. Now, let's see what we got
That's
here.
one question though. I skipped out the graphing part.
All right, well, let's find the sum anyways. Consider the following. N equals 1 to infinity. We have 4, 0.9 to the n minus 1. And the thing to do is generate a couple of terms here and see what's going on. When n is 1, I've got 1 minus 1, which is 0. I've got 4 times 0.9 to the 0. I have 4. Okay, plus. All right. When n is 2, I'll have a 4 times 0.9 to the first. And when n is 3, I'll have 4 times 0.9 squared, etc. Okay. That's what I'm going to have. That's my series. It's geometric. R is equal to 0.9. Has an absolute value less than 1. Consequently, this geometric series converges. The sum is equal to A, 1 minus R, which is 40. Okay? The sum of that series is exactly 40. And what does that sum of that infinite series of 40 means? It means as you add the terms, that sum is going to get closer and closer and closer to 40. How close to 40 does it get? It gets arbitrarily close. Does it get to within 1 of 40? Yeah. Does it get to within a tenth of 40? Yes. Does it get to within a hundredth of 40? Yes. Within a billionth, a trillionth, whatever small number you want to name, it gets to within that small number of 40. And it never goes past 40. Okay? It's kind of interesting. Now, the rest of this stuff, it says use a graphing utility to indicate the partial sum and complete the table. All right. Here's what you should do for that. For the first one, it says n equals 5. I would have Mathematica do this. Mathematica will do this quite well. Just write it in just like that. Okay? Have the sum, use the summation notation from 1 to 5. It'll give you the sum. That's what they want you to do with a graphing utility. Okay? And if you do this, you'll get these sequence of partial sums. This will be the sum of the first 5 terms, and that sum is going to be something or other. Okay, maybe 30-ish or something. Then you do the first 10 terms, it'll be like 35-ish. And then maybe the first 20 terms is like 39. And then the first 50 terms, 39.5.
No, 20 is like 36, and 50 is like 39, and 100 is 39.89, 99.89.
What is the last one?
It's
39?
39.9989.
Ha! That's pretty cool. All right, so you can see, it's what I said. These are going to get closer and closer to being a sum of 40. So did you do it with Mathematica?
No, on my calculator.
On your calculator? Well, calculators nowadays can do such a thing. The computer algebra system would be an easier way to do it. Although you have this notation in your calculator, you can just do it like this, or you have to actually.
Yeah.
Oh.
I added
Oh,
and
oh.
changed the power.
Oh.
It took me like 5 minutes.
That's not too bad, I guess. But anyhow, I would recommend a Mathematica. But like she said, you
But
could
I
do.
wanted to ask him, like, is there any easiest way to do
Yeah,
it?
Mathematica is the way to do it. And that's the way to do it. And what happens is, this thing, the sum, the sequence will approach 40.
Holy crap, mine does.
You have the summation notation?
Yeah.
Oh, that's cool. All right, so there you go.
And that's a scientific calculator.
Yeah, well, I'll tell you that the calculators, they can do things. All right, they can do a lot of good things. What do you get for this sum? You got like,
Right now.
30, what'd you get?
What do I
30?
gotta do, x
Well,
minus
for the
1?
first one,
Yeah.
45, it was like, I don't remember.
Well, Trent's going to get it right now. Oh, what'd you get?
1.
And that's not right.
No.
Fancy calculator. Well, I don't know if I'm using it right. Just know it's a sum. It's on here.
I
They need
have
like
it
a
done on
textbook
the
for
web
this thing.
assignment, but I didn't write on the paper.
Yeah,
I know
yeah.
exactly.
Cool.
5,
Well, there you go.
1. Hold on a second.
Why need mathematical when you can use a calculator?
Let me see if we can get it.
They should make a mathematical calculator.
I might get it by the end of class.
Oh, all right. Well, I'm not going to wait around. But you can do it. Calculators can obviously do it. And but my recommendation, of course, is to use a Mathematica to do it. Yes.
Only
You have
example.
another one? Like,
One like this?
16.
no, a similar one. I remember.
Go ahead.
4 over n
Actually, that sounds about right.
times n plus 3 in
It's like this
parentheses.
one?
Times what?
Yeah, similar to n plus 3 in parentheses in the denominator.
It's similar to
Yeah,
that
this is
one.
very again.
Birds.
Oh, got it. Okay. That's fine. It's fine. This one here, and you're starting in at 1 to infinity.
Yeah.
This is a different sum. Okay, this is a different problem. This is not a problem. This is not a geometric series anymore. This is a telescoping sum. This is what we did the other day in telescoping sum. I can do this out. Let's do it out. What do you want to do here? You want to take this and you want to split it up with partial fractions. Okay, so let's do that. Okay, let's take this 4n plus 3, and you'll have an a over n and a b over n plus 3. Okay, solve for a, multiply by n, let n equal 0. Okay, a is 4/3. Solve for b, multiply by n plus 3, let n a. Was it? Oh, you said 20 minutes. That was just about exact. Wow, pretty cool.
Yeah, you should have come in 3 minutes later.
Multiply by n plus 3, let n equal -3. You get -4/3.
There's a box.
I don't know where the box is. There's no
No,
box.
he just brought it.
Oh, he brought the box. Oh, you made a box. All right, fine, whatever. Yeah, good deal. All right, once you do this, then you realize that this can be written this way. 4/3 over n minus 4/3 over n plus 3. Am I still there? Yeah, I'm still right there. Now, the 4/3 you can take out front. And I'd recommend it, just to get it out of there. Okay, this is what you have. Now, if we write out a few terms, first of all, as we saw last week, we're going to write out some of these terms, okay? The terms in the middle are all going to cancel out. We're going to be left with 3 terms in the beginning. And you know that because if you take n plus 3 minus n, you get 3. That tells you how many terms will remain in the beginning. You will also have 3 terms in the end. But those 3 terms in the end do not matter because they're going to go to 0. We don't care about those. The only things that matter here are the 3 terms in the beginning that remain. So if you do this out.
But that's for only these type of problems?
Yes, correct.
For, what is this called again?
These are called telescoping sums.
Okay, so
And they're
it's only for telescoping.
Yes, it's only for telescoping. So let's see what happens. You got 4/3. Now when it's 1, you get 1 minus 1/4. When it's 2, you have 1/2 minus 1/5. When it's 3, you'll have 1/3 minus 1/6. Okay? Now those are the 3 terms you're going to have in the beginning. Now watch this. When we get the next one, 4, we got a 1/4 now. 1/4 minus 1/7. Plus. Those will keep on going. Okay? You'll get 3 at the end, but they're going to go to 0. We don't care about those. What happens here is the 1/4 cancels out the 1/4. The 1/5 will get canceled out by the next term. The 1/6 will get canceled out by the next term, etc. The only thing that will remain will be the 1, the 1/2, and the 1/3. And when you go to 6 on those, you get 6 plus 3 plus 2. You get 11, 6. So we'll get 44, 18, 22 ninths, apparently. Okay? So the answer should be 22 ninths on that one. Okay?
What's the point about adding all of those up?
You add these up to find the actual sum of the series.
Oh, just the
Yeah,
sum. But
that's the sum of the
What do you do with the sum?
Well, there are applications for infinite series, and DiffEqs, there are some differential equations where you have no other solution other than solve and get an infinite sum.
So you find that sum and do
And do-
something else with it?
No, well, yeah, it's the solution to a differential equation that may be a circuits problem. Those kinds of differential equations are a little bit more complicated than the usual circuit problem. So I'm not sure what those applications would be. It could be some kind of chaos kind of a thing, actually. But they are used. They are used. Oh, and infinite series will be used at the end of what we do in a couple of classes. The infinite series are used to approximate things like sine x and cosine x and log x, and those things are infinite series as well. Now, they're not quite like this, but they are infinite series that we will use to approximate things. And that happens in a little bit, in a couple of classes. All right, everybody else set on this? Is this?
Yeah.
Okay. Are we okay with this? Okay. Any other questions on homework?
Get started.
Let's get rolling.
So you're saying this is a long one?
Well, we're talking 8-ish, you know, the usual kind of time. You know, right in there somewhere.
7:30.
Hey, we'll see. All right. First thing, now here's what we're doing. We're doing tests for convergence. We've got 2 series where we actually find the sum. Geometric series, telescoping sums. Those are 2 series where we actually find the sum. The next set of things that we do with infinite series are merely to determine whether the series has a sum or not. We're not even going to find the sum, but we want to know, does it have a sum? Okay? Does the series converge or not? These are tests for convergence. Okay? And the very first test we have is this one. This is called the nth term Divergence Test. It says this: given an infinite series, okay? And all the series we're talking about are infinite series here, okay? Given an infinite series, then if the limit as n goes to infinity of a sub n is not 0, if the nth term is not going to 0, then the series diverges. Very important test. But it's easy to get messed up on it. Here's what it says. If you have a series, here, let's take a series. Let's take something like this. Here's a series. Here's a series. What's going on with the nth term? What's the limit as n goes to infinity of this nth term?
It's infinity to infinity, infinity over infinity, which is the name is
L'Hopital.
L'Hopital's rule.
We can use L'Hopital on it, and what do we get after using L'Hopital's on this?
You find the derivative.
Yeah, yeah.
So so you find derivative n, which would be 1. So, and then you have 1 on the bottom too. So it's a 1 over 1, so equals 1.
Perfect. That limit is equal to 1. Okay? That limit is equal to 1. All right? So here we have a series where the nth term is going to go to 1 and not 0. What can you tell me about this series?
It's always 1.
Well, we got a whole bunch of terms we're adding up. The terms are getting closer and closer to 1.
When do we converge to 1?
The terms do. See, this is where it gets confusing. If you had a sequence, n over n plus 1, the sequence would converge to 1 because that nth term has a limit of 1 as n goes to infinity, as Nick just said. But if a series has its nth term going to 1 and not 0, that tells you that the series diverges. After all, what happens if you add up an infinite number of things close to 1? You're going to get infinity. That sum is going to increase without bound as you add up these things that are getting closer and closer to 1, and you add an infinite number of them. That sum will go to infinity. This limit is 1. This series diverges. If you have any series where the nth term is not going to go to 0, the series will diverge. Okay?
Okay, so if it's not 0, it's going to, even if it goes to, say, 5?
Doesn't matter. As long as the nth term does not go to 0, the series will diverge.
Okay.
Now, that could be confusing there, but it's even more confusing if you have something like this. Let's take a look at this one. Let's look at this one. 1 over n. What happens to 1 over n as n goes to infinity?
Goes to 0.
It goes to 0. What does this test tell us about this series? Be careful.
It diverges because it goes to infinity, right?
No, you just said the nth term is going to go to 0.
Oh, okay. Then it goes to 0.
The nth term goes to 0. Does the series converge or diverge?
Converge.
Here's what this test tells us about this. This test tells us nothing about this series. Here's what the test says. If this nth term is not going to go to 0, we know the series diverges. We just used that fact in this one. But if the nth term does go to 0, the test tells us nothing. Okay? It's an if-then statement here you got to be careful about. Okay? It says if the nth term is going to go to something other than 0, I know that series diverges. But if that nth term goes to 0, the series may or may not converge. It will converge as long as that term goes to 0 fast enough. If it doesn't get there fast enough, the series will diverge. This series right here diverges, even though the nth term does go to 0. But this series, let me just give you this. This nth term does go to 0. It gets there quicker, gets closer and closer to 0 faster than 1 over n does. This series converges. Each series has an nth term going to 0. This one doesn't get there fast enough. We need another test to determine whether it converges or diverges. The same with this. And the test we're going to need is what's coming up right now, the integral test. But go ahead.
Never mind.
Okay.
So I was going to ask how
All
do
right.
you know it's going fast enough?
Yeah, well, that's it. That's what all these other tests are going to be for. But
So
the
anything, so
go ahead.
anything, so does it matter, does the, what is it called, have to go to infinity for this test to work?
Yeah, all our series will go to infinity. We have infinite series, every one of them.
For every one of them?
Every one of them.
Okay.
We have nothing but
The
infinite series.
telescoping ones and,
Those go to infinity, geometric go to infinity.
so all the other stuff that we've been doing doesn't converge technically to 5, doesn't converge to, they're all.
All right, wait a second. You got to be very careful here. All right, hold on. Well, I want to be. Let's be exact. Let's be exact. You've got the terms themselves. Those terms in a geometric series, those terms in a telescoping series, all go to 0. Any one of those that we've done today. What happens to these terms? They will go to 0. These terms go to 0. You'll notice they're getting smaller and smaller and smaller as you increase the exponent here. When you increase the exponent on a fraction less than 1, it will go to 0. Okay? It's going to go to 0. These terms go to 0. What do these terms do? These terms go to 0. Okay? That's true for any series that converges. The terms must be going to 0. These terms do go to 0. They just happen to be two series where we can actually find the sum. Now, terms going to 0 and series, there's two separate things here. See, when you use the word converge, you've got terms converging to 0, and you also have series that have a sum. This series sum was 42. Okay? Okay. The terms are going to 0. The series converges to 42. But the terms converge to 0. So you got to be careful and make that distinction. All right? A little tricky, but you guys can do it. All right.
Can we use that next test for those, on those homeworks to see if they go to 0 quick enough?
What test? This?
The next one?
Yes, the integral test?
Yeah.
For some of them you can. And then we'll have more tests because we can't use, there's no one test that works all the time. That's why we have the integral test coming up, and then we're going to have a limit comparison test, and then we're going to have a direct comparison test, and then we're going to have alternating series tests, and then next class we're going to have ratio tests, and then we're going to have root tests. So that's the way it is. But, like I said, I'm going to give you a couple of shortcuts that will mean that you can do a lot of these problems, almost all of them, just by looking at them, okay? Just by looking at them. I got to give you the tests first, though, okay? I got to give you the tests first, but then I'm going to give you a couple of shortcuts that you can use, okay? Okay, that's the nth term divergence test. That's generally what you're going to do first. When you have an unknown series to analyze, what do you do first? Check to see, are the nth terms going to 0? If they're not going to 0, you're done. The series diverges. If they do go to 0, you're not done. Okay, you got to use another test. All right, you got to use some other test to see if they're getting to 0 fast enough. Everybody understand that distinction? Okay. All right. Let's do an integral test. Given series where each of these is positive and decreasing. The terms must be positive and decreasing. Then, the integral from 1 to infinity of this in terms of x, of the nth term, okay? We're going to write it in terms of x. I'm going to write it in terms of n here because this will be expressed in terms of n. Then this integral and the series, okay, converge or diverge together. Okay? So here's what this says. Let's take this one. Let's take the one I just gave you. Which is 1 plus 1/2 plus 1/3 plus 1/4, etc. This is called a harmonic series, by the way. Okay? It's a harmonic series. Let's take a look at it. First of all, is the nth term going to 0?
Yes.
Yes. Oh, well, that means we're not done yet. That means we're going to have to do something else. There's something else we're going to have to do. We're going to test this with an integral test. We're going to take the integral from, 1 to infinity, 1 over x dx. Okay? It's an improper integral. We know how to do that. We take the limit as b goes to infinity, the integral from 1 to b, 1 over x dx, and we see what happens here with this integral. If the integral converges, the series converges. If the integral diverges, the series diverges. So let's do it. Limit as b goes to infinity, integrate it, natural log. Oh, and speaking of natural log, people, when you use natural log in Mathematica, natural log, okay? The log function is a Mathematica function. If you're going to use Mathematica's function of natural log, please, you have to start with a capital letter. And it's not just ln, it's the capital LOG, square brackets to enclose the argument thing. Okay? So if you want to do the integral of the natural log of x, okay, which is what the part of the lab was, you have to have the integral of capital LOG square brackets x dx. If you want to do secant x and do the integral of secant x, secant's a Mathematica function. How do you reference secant? Capital S, EC, square brackets, X, end of square brackets. Okay? Just so you know. All right? And if you want to do e to the negative x squared and do that integral from negative infinity to positive infinity, which Mathematica will handle very well, but you've got to make sure you use the right e. You've got to use the e in the palette. It's a specially designed e for that. You can't use the e from the keyboard. That doesn't work. Okay, that doesn't work. So just be aware of that, all right? Okay, so integral of 1 over x, natural log. Take the limit, b goes to infinity, natural log of b minus the natural log of 1. Well, the natural log of 1 is 0. As b goes to infinity, where's the natural log of b going? Infinity. Okay. Which means this integral diverges. It goes to infinity. Consequently, the original series diverges. Okay?
Wait, so the natural log of infinity is infinity, right?
You bet it is.
Okay. What about e to the x?
If you had an e to the x thing here,
Yeah.
and you integrated that,
Yeah.
and you let n go to infinity, and you end up with e to the n, definitely goes to infinity. Okay, it increases rather quickly.
Okay, and natural log of 1 is 0.
Correct. Now, this is amazing that series, that harmonic series, diverges. If you do this in a computer, okay, and it does, do Mathematica. Take n equals 1 to infinity. You can't take 1 over to infinity because it'll tell you it diverges. But if you take 1 to 1,000, you'll get a number here. You'll get an answer. And you take 1 to 10,000, you'll get an answer slightly bigger. And then you take 1 to 1,000,000, you get an answer slightly bigger. But you're adding on these little teeny tiny terms. But guess what? That sum gets greater than every positive real number. It takes a lot of terms to get there, but it eventually gets greater than any positive real number. It's amazing. And computers I've never seen a computer do anything past like 12 or 13. If you actually put it in here, I don't know, that was a few years ago. We did one where we tested it out. But I don't know about today's computers, but no computer can handle those small numbers like that. They'll eventually truncate them to 0, and the sum will not increase anymore. But the sum is increasing. As a matter of fact, it keeps on increasing and gets greater than every positive real number. Okay? It's amazing stuff. It's incredible. All right, there's a series that diverges. That's a very important series, diverging series, because we're going to be using that a lot when we do the comparison tests that are coming up. But I want to do another integral test. Okay, you ready? Are you doing this one on your...
Trying.
Yeah? I'd be curious, or if you can...
Like to 1,000, you said?
Yeah, go to 1,000 and see what you get for a sum.
It's loading.
Okay.
Tell it will be
Still loading.
I don't know what it is. It's not a big number, though, I don't think. It's a pretty small number. You're adding up 1 plus a half plus a third plus a fourth plus a fifth, dot, 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 up to 1,000. Hey, Danielle, how you doing?
Loading.
So you played today?
It
Yeah.
might.
You pitched?
Man,
Wow. How'd you do?
we won.
Wow.
I was 100.
Wow. A grand slam against it? No. Oh, that's good. That's good.
Yeah, 1 to 1,000 is too big.
Oh, it's too. Oh, really?
We'll do 100.
Do 100. Yeah, that's gonna be a small
I
one.
know in Java, like
I'd like to see a Java program.
5.18.
5.18. Okay, that's out to 100. You get 5. If you go out to 1,000, you may get 50. I don't know what you get. You get something. I don't care what language you're using. The problem is the internal representation of numbers in the computer. Even if you use double, you know, like 32, long integer, long. Geez, I used to know all the jargon when I was doing it in programming. And when I was doing machine code a long time ago, I used to know all those, but I don't know them anymore. So anyhow, eventually they can't handle the smallness of the numbers and they truncate to 0. And then they don't make any more progress. All right?
well, see, the thing is, if it takes it long enough, it's gonna like take up a bunch of your RAM.
Oh, yeah.
I think, and then I've done numbers like that where you put it to a certain amount and it just keeps doing it
Yeah,
over and
yeah,
over and over
yeah.
and over again.
Well, Mathematica gives up after a while. It'll say it's exceeded the number of iterations allotted for this process or something like that. And it'll just say, this is as far as we got, this is the answer. What we're doing, Danielle, is doing tests for convergence, okay? We're given an infinite series. Now, last time what we did, we found the sum of 2 kinds of infinite series. Geometric series and telescoping sums. And we actually found the sum. But now we're just determining whether the series has a sum or not. We're not even finding the sum. And one test we have is what's called the nth term divergence test. It says this: if you're given a series and if the nth term is not going to go to 0, if that's not going to go to 0, the series will diverge. In order to have a shot at converging, the nth term must be going to 0. But some series have nth terms go to 0 and still diverge. They have to go to 0 fast enough. But one thing you do know, if the nth term doesn't go to 0, the series will diverge. Okay? And now the next thing we just did is an integral test. You can have these notes, obviously. And what do? You take the series in question. This is called the Harmonic Series for its relationship to music. And you identify an integral with it. You take the 1 over n, replace it with x, and you go from 1 to infinity. If the integral converges, the series converges. If the integral diverges, the series diverges. This integral diverges, goes to infinity. Therefore, the series diverges. And this is what we're discussing. That means this sum gets greater than every positive real number. It gets greater than 1,000,000 or 1,000,000,000 or 1,000,000,000,000. And it takes a long time to get there. Okay? Hey, Vitaly. So that's what you have. That's what we're doing right now. And I'm going to use the integral test in another series right now. You ready?
Not to explain it for Todd.
What's that? I'm not going to go over that. Danielle lucked out. She came in first. She got the recap. But Vitaly, you're going to have to get it from somewhere else.
YouTube.
What's that? YouTube. Yeah, get it from YouTube. Everything's on YouTube,
All right,
right?
he'll put it on, he'll be putting this up anyway.
All right, here we go. Let's do one more integral test. Let's do this one. Let's test this series. Okay. 1 over n squared. What is this series? This series goes this way. It's 1 plus 1/4 plus 1/9 plus 1/16 plus etc. What's the limit as n goes to infinity of 1 over n squared? Where are these terms headed? The terms of this series are headed where? What's this limit? Here, write it out. What's the limit here as n goes to infinity?
This one dies.
0.
This one diverges.
Yeah. This one goes to 0. The other one went to 0. But this one gets to 0 quick enough. Okay? This one will converge. And we can prove that with an integral test. So let's do it. Let's do the integral test. Sorry about that. Okay. And all that means is replace the n with an x, go from 1 to infinity, and let's see what happens with the integral test. Okay. Integrate x to the negative second, add 1, divide. I'm sure we've done this one. When we did improper integrals, we must have done this one. Rewrite it. This is probably on your test, as a matter of fact. Substitute in b. Minus minus plus 1. As b goes to infinity, this is going to go to 0. That's equal to 1. Therefore, the integral converges, and consequently, the series converges as well. Now, you've got to be a little bit careful about this. We have proved that that series converges. The integral has an answer of 1. That does not mean that the series has an answer of 1. Okay? And obviously it does not. The series does converge, but it converges to something greater than 1, obviously. Okay? But we do know that it converges, and that's all we want to know. We want to know, does it converge? What's that?
Doesn't it converge to 0?
Now, see, you got to be careful here, Nick. And when you say that, the terms converge to 0. The series converges to some number greater than 1. That number, by the way, is, believe it or not, pi squared over 6. Okay? It's amazing how that series can converge to pi squared over 6, but it does. Okay? But we don't care about that. We care that since the integral converges, that series converges as well. Okay? Is that reasonable?
Yes.
Okay, now, what about something like this? Let's take another candidate for an integral test. Let's take a look at this series. Let's see, what do we have? We have 1, we got 1 over e. 2, we got 1 over e. This is just too easy. Sorry. I was thinking of this as an integral test candidate, but it's not really. What kind of series is this?
Telescoping?
What is it?
Is it telescoping?
No.
Harmonic?
No.
Geometric?
Yes, it is geometric. Got away.
That's how they want it.
Yeah, to be telescoping, it has to have those 2 linear factors down below.
Oh,
This
right.
doesn't have that. This is geometric.
I was just thinking.
All right. This is geometric where r is equal to 1 over e. And since 1 over e is less than 1, we know that this series converges. Not only that, because it is geometric, we know what the sum is. I was thinking I would do an integral test on this to prove it converges. But we can do better since it is geometric. Not only do we know it converges, we know what the sum is. Okay? So that one's pretty simple. All right?
So the sum on all of them that are less than 1 is a over 1 minus r? Is that the sum?
That is the sum. Yes, where the ratio R has an absolute value less than 1.
Right.
Yes, yes. All right, so here's the deal. Suppose we have series of this type. These are called P series, by the way. Series of this type. That's a P there. These are called P series. 1 over n, the harmonic is a P series where P is 1. 1 over n squared, P series where P is 2. What can we say about P series? Here's what we can say. Since we can use an integral test on this, we can say this. If P is greater than 1, the series will converge. And we could prove that with an integral test. If P is less than or equal to 1, that series will diverge. Okay? And again, we can prove it with an integral test. Okay? So, let's take a look at a couple of these P series. These are very important series, they're very common, and they're what we're going to use to compare other series to. So if you had something like this, everybody okay with this? Any questions on this? We all okay? Okay. Where is she in the day? Yeah, just
anywhere. I've been home.
Oh.
House I've been to.
Okay.
So if P is greater than 1, it converges. If it's less than or equal to 1, it diverges.
Yes. You ready? Let's do it. Let's take a look at this series. Let's do 1 over the square root of n. Okay? First of all, let's just write out some terms. We got 1 over the square root of 1, 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, etc. What's the limit as n goes to infinity of 1 over the square root of n? Where are these terms going?
Wait, is that square? We call it becomes
To
2.
infinity, or 0.
It's going to 0. That limit is 0 because the denominator is increasing without bound and the numerator is stuck at 1. These things are getting smaller and smaller and smaller. They're going to 0.
Say by integral.
What's that?
Integral?
Yeah, here's the deal. Since the terms are going to 0, it may or may not converge. It depends if they're going to 0 fast enough. How do we determine if they're going to 0 fast enough? We'll do an integral test.
The P term.
Well, we can use the P series. The P series says what?
That the
Less than-
exponent, right?
That exponent is equal to 1/2, which is
Less than 1.
less than 1. So that P series says it's going to diverge.
No, if it's
Yeah,
negative,
and that's
doesn't
true.
matter.
What's that?
If it's negative, doesn't matter.
Yeah, if it's negative, I'm going to do one right after this. It's less than 1, it's going to diverge. I'm going to prove this with the integral test. I just want to verify it with an integral test, okay? So let's take a look at this. Let's do an integral test just to convert, confirm what we already know. 1 over square root of x. X to the negative 1/2. Add 1, divide from 1 to b. Take the limit, b goes to infinity. 2 square root of b minus 2. Now what happens here is b goes to infinity. Where's its square root going as b increases without bound? Infinity is correct. Therefore, it will diverge. Because the integral diverges, goes to infinity, the series will diverge. But we knew that from the P series. What happens if P is negative?
Is it a negative in this one?
What's that?
Is it a negative in this one?
Well, it turns into be, P is actually 1/2. You're right, it's 1 over n to the P.
Oh.
P here is 1/2.
It's in the
Yeah.
denominator.
Yes,
It
yeah.
has to be negative in the denominator.
Yeah, let's make a negative in the denominator. Let's suppose we have this series. Let's take a look at this series. Now P is negative 1/2. Well, let's see. Let's rewrite this thing. Now, I could use an integral test on this to prove that it diverges. I don't have to. Why? As n goes to infinity, where is n squared going? To infinity. Not going to 0, going to infinity. I know this diverges right now. And I don't have to use an integral test on it because n squared, that term is going to infinity as n goes to infinity, not going to 0. So I know it diverges. I also know it diverges because it is a P series where P is negative 1/2, negative 2, which is less than 1. As long as it's less than or equal to 1, diverges. Go ahead.
You can't use the P series when it's in the numerator.
No, you have to be able to write it this way to be a P series. It has to be 1 over n, just like this, 1 over n to the P. Okay? Now, if P is negative 1/2, you rewrite it this way, and now the thing is not going to go to 0, so it diverges. Yes?
It doesn't go with, you said it equals 0, it's not infinity?
Say what again?
You said at the very top, you said the limit, yep, it's 0, it's not infinity?
As n goes to infinity, the square root of n is going to go to infinity, increase without bound, and its reciprocal will go to 0. Okay, it will go to 0. However, what we showed here by using the integral test, it doesn't go to 0 fast enough to cause the series to converge. Even though these terms are going to 0 because they're decreasing, we got 1 over the square root, they don't go to 0 quickly enough. That series will diverge. It's a P series where P is 1/2. Not good enough. In order to converge, the P has to be greater than 1. That'll cause those terms to go to 0 fast enough to cause it to converge. Okay? Okay. What's that? Yeah, all right. As long as Nick gets it, I'm going on, man. All right, now. Let me give you a couple. You just tell me, converge or diverge?
Converge.
Converge or diverge?
Diverge.
Diverge is correct. Why? What's P? 1/3 is correct, and that's less than or equal to 1. Less than or equal to 1 is the key. What about this series? I'm waiting for Nick to say something, so I'll do the opposite.
I don't get it.
All right, never mind. That's okay. What about this one?
Converge.
Converge. What's P? 3. Converge. Nice. Okay? Where P is equal to 3/2, greater than 1. As long as it's greater than 1. What about this one? It converges. Okay? It converges. Very, very slowly, but it does converge and has a sum. Okay? And has a finite sum. All right, how are we doing? Integral test?
Okay, we got a couple more tests.
Oh, yeah.
Professor,
Yes.
on like the exam, would you just ask us if that diverges or converges?
Yep. That's exactly what I will do. Like I said, on the exam, there's a couple where I ask for the sum. I'll give you a geometric. I'll give you 2 geometrics, I believe, and I'll give you 1 telescoping. So I'll ask for the sum. So you're going to have to do what we did for those. But then the next 8 or 10 questions are, does it converge or diverge? And most of those you'll be able to just look at and say converge or diverge. Okay, it won't be a big deal. Okay? Is everybody okay? All righty. I'm going to go on. There are two comparison tests that we have. The first one is called a direct comparison test. Let's say we're given these terms of two series. Okay? We're given these terms, A sub n's and the B sub n's. A sub n's are less than or equal to the B sub n's, but they're all positive. They're all greater than 0. Okay? Then, if the series of A's diverges, the bigger terms, the B series, diverges as well. Okay? The B series consists of greater than or equal to terms of the A series. The A series diverges, goes to infinity. Therefore, the B series must go to infinity as well and diverge. If the bigger series, the B series, converges, the smaller series also must converge as well. Okay? How's that? You ready? Let's suppose we have something like this.
So they're direct.
This is a direct comparison test. You are comparing these two series directly with each other. Okay?
So what I'm saying is that they move along the same.
Yes, they do. Yes, they do. Let's do one. Let's suppose we have this series and this. So I have to have them. Yeah, well, that one's diverges, so I need a bigger series here. Let's do 2 over n here. Okay? Now, you know this is a known diverging series. This is the harmonic series. It's a p series where p is equal to 1. We know it diverges. This series, 2 over n, now what you could do is just take the 2 out front and get a harmonic again, because you can always take the constants out
Being
front.
the good person that I am.
Oh, you brought them? You went to get them?
Yep.
Are they still piled up?
Oh, they're gone.
Oh, so it's too late now anyway.
I can do them and seal them and put them in the envelope tomorrow.
Oh, that's true.
Put them in the
Good.
mail tomorrow. They'll take it tomorrow.
All right.
He's leaving.
Who is? He's sick.
Oh, no, never mind. Now, don't talk to me.
The box is already gone?
Yeah, what is it, though?
I don't know what happened.
Leaking here?
I guess. All right.
That's their fix.
is
Put
about
a
leak.
bucket underneath it.
Go scrape some of that stuff, the asbestos there.
Yeah.
I'll go
It's
take-
I'll go-
It's the best one.
Yeah, just take a deep breath when you're doing it.
Yeah, good. You
Yeah,
did.
an oatmeal.
Next take a gunfire on it, color shots there. Get some dust there.
All right, thanks,
I
Ian.
ripped one of them, the bottom one, I ripped the envelope. It was stuck in your box.
Oh, yeah, that's all right. No biggie, thanks.
No problem.
Z, is your class over already?
Oh, you couldn't know.
He goes one time, he goes one. All right, but anyhow, well, it's up to you guys.
Not doing it all.
We can do it now, we can do it Thursday.
You can mark them all. Yeah, just mark them all good.
Yeah, this is so fun. Do they even do anything with that? I highly doubt it.
Can we just do it Thursday, please?
We can do it Thursday.
Because that's worse.
We'll do it Thursday at the beginning class.
Yes, thank you.
Do they do anything with it? That's a very interesting
I don't
question.
think they do.
Yes, they do. We get a report, I get a report back in a few
Yeah, it's got a good
weeks
one up there.
saying what my rating is. Now, do they do anything with that rating? I don't.
Unless like you got really terrible.
If you get terrible ones, my understanding
They might
is
look into
Dean will talk to you.
Yeah.
You will get a, What's that? Has anything ever happened to anybody? I don't think so.
No, I don't.
I don't. But I don't know. We'll do it Thursday before class. Okay. Here we go. Harmonic series, diverging, known diverging series. Not quite harmonic because of the 2 up there, but we could change it into a harmonic by taking the 2 out. But because the 2 is up here, let's leave it there. What do we know about this series? These terms are greater than these terms. Okay? This is a bigger series. It's bigger than the known diverging series. If it's bigger than the known diverging series, okay, the series would be the A sub n series. This would be the B sub n series. Then we know that this one diverges as well.
How do you know it's bigger or not? That's what I'm saying.
Because you got a 2 in the numerator, it's twice, each term is twice the size of each of one of these terms.
They're going to be harder than that, right? Knowing
On WebAssign,
or do you just have to put a 1 in and you'll know?
yeah, basically, you know,
Just put a 1 in, right?
you know, in a couple minutes, I'm going to, when I do the limit comparison test next, then I'm going to give you one of my 2 shortcuts, okay? Where you can, it just won't matter. You'll be able to look at these and just say it converges or diverges. Okay, is this reasonable here? This should be reasonable, I would assume, okay? And the same thing works if you had something like this. 1 over n squared is 1. And the other one you had was 1 over n squared. Well, this one's kind of interesting, actually.
So that one's bigger.
Well, okay, this is a known converging series. It's a p series where p is 2. How are these terms related to those terms?
They're not small.
They're smaller, because when you add 1 to the denominator, the terms are smaller now. The denominator is bigger. The terms are smaller. So these terms are less than these terms. Okay? So this is a converging series.
Yeah, but it's less.
These terms are less than these. Here's the deal. The B sub n would be these. The A sub n would be these, the smaller terms.
Oh, so you can move
The B
them
sub n, yeah.
Okay.
Since these converge, this converges, these smaller terms must converge as well, because they're smaller.
No matter what the order they're given.
Yeah.
So technically speaking, you don't even have to look them up because they're always either going to be equal to or greater, and one of them's going to have to.
Yeah, that's true. But here's the deal. Okay, everybody else other than this. Okay? Everybody's okay? That's a direct comparison. Let me give you the limit comparison test, and then I'm going to give you the first of the 2 shortcuts.
So you can look at technically any one of them, though. If you find that one's converging, that means the other one's converging.
Well, it depends. If the bigger one converges, then the smaller one will converge. But if the smaller one diverges, the bigger one will diverge as well. So it works 2 ways. You got to be careful. All depends on which the known series is. Here, this one here, for example, known diverging. Oh, terms are bigger? That must diverge as well, because these terms are bigger than these terms. Known converging. Oh, smaller terms, therefore it must converge.
I thought it didn't matter, but not really.
It doesn't really matter. I'm going to give you a trick there. You don't even need that. All right. Doesn't even matter. Let me give you a limit comparison.
So we know how to do it.
Limit comparison.
It's like accounting.
Given two series. Am I off the page? Whoa. Limit comparison test. All right, limit comparison. Given 2 series, B sub n, then let, oh boy, I'm getting real sloppy now. That's let, I know, that's let. Let the limit as n goes to infinity of a sub n over b sub n equal L. In other words, you're going to take the nth term of one over the nth term of the other. And and take the limit as n goes to infinity. Okay? Let that limit equal L. Then, if L is real and L is greater than 0, in other words, the limit exists and is greater than 0, then the series will converge or diverge together. So if you take the nth term of each and take the limit as n goes to infinity, and that limit exists, is some positive real number, the two series will converge or diverge together. Because what does it mean? It means that they're increasing at about the same rate. Okay? And if you know one converges, then the other one will converge as well. That means if you have something like this, let's take a look at this series. What about this series? Whoa.
Don't you need two?
What's that?
Don't you need two?
I'm sorry.
Don't you need another one?
Oh, we're gonna figure out what the other one is.
Oh.
Yeah, we do need another one. Now let's take a look at this. N over n cubed plus 1. What's critical here is the difference in degrees. Okay, that's what's critical. And what we can do, since the difference in degrees is 2, what we're going to do is compare it to this known converging series 1 over n squared. And the limit comparison test, let's do it. Let's do a limit comparison test. Let's take the limit, n goes to infinity. It doesn't matter which one's the a or b. Just take one term over the other term. Okay. Let's do the limit. Let's multiply by the reciprocal here. This becomes the numerator, and you get n squared times n cubed becomes the denominator. Now, what's this limit as n goes to infinity of n cubed plus 1 over n cubed? 1. Was that you?
Yeah.
Wow. Good, Danielle. All right. N cubed plus 1 over n cubed is 1. That's greater than 0. It's real. Therefore, the two series converge or diverge together. This converges. This one does. What's that?
Is it because n cubed cancels out?
They don't really cancel out. They're same degree. You can use L'Hopital's a couple of times. One thing you do in Calc 1 is if these are of same degree, the ratio of leading coefficients is the limit here. You can divide numerator and denominator by n cubed if you want. Yeah, there's a couple of ways. That limit is equal to 1. Now here's the key, though. Here's the first important trick, where you can do half these series with this one trick. I swear it's about half of them. All right. Given. Let's say we got, oh boy, oh man, I'm losing it here. Jeez. All right, given that series, wow. Okay, let's say the top one is n to the k plus n to the k minus 1. It's written in descending order, and you got all kinds of stuff here, down to some constant. And this series is like n to the m plus n to the m minus 1 plus all the way down to some constant down here somewhere. Okay, so you've got this rational expression here. The key to whether this thing converges or diverges is the difference in degrees. If m minus k, if m minus k is greater than 1, then converges. Otherwise, else diverges. Okay? That's all you have to do is look at the difference in degrees, numerator and denominator, okay? If that m minus k is greater than 1, it's going to converge. And how do you know that? Because you can do a limit comparison test with that series with the corresponding p series, where p is equal to m minus k, like we just did with this one here. 1, 3. Difference in degrees, 2. Greater than 1, done. Converges. We don't even have to do this. Okay? It's guaranteed. So,
What did that one mean?
which one?
Yeah.
This one right here?
Yeah.
The fact that that's equal to 1 tells you that that limit right here is real and greater than 0. It tells you the two series converge or diverge together. And since it was equal to 1, we know they converged together. Since this one converges, that one must also converge. But it's the difference in degrees that's important. It's all that matters here. So if you have this one,
Is M always in the denominator?
well, the greater one has to be in the denominator. Because if they give you, if you had something like this, this series, will it converge or diverge?
This will diverge.
This will diverge because the difference in degrees is -1. You always do m minus k. And it's 2 minus 3 is -1. That's not greater than 1. Okay? These terms, by the way, as n goes to infinity, are not even going to go to 0. They're going to infinity. That tells you it diverges right from that. Okay?
So it diverges if it's equal, less than or equal to 1.
Correct.
Okay.
So, diverges. What about this one? What will that series do? What will it do?
Converge. No, this will diverge.
Diverge.
Because it's equal to 1.
It's equal to 1. Diverge. This and its reciprocal will both diverge.
Why does that one diverge?
Because that difference in degrees, 3 minus 2 is 1. Not good enough to cause it to converge. It will diverge. And how would you prove that? You would prove it by doing a limit comparison test with the harmonic series 1 over n. And you would find that that limit does indeed exist. So this series and the harmonic series 1 over n diverge together. Okay? You with me? Okay? How about this one?
This will converge.
Converge, because the difference in degrees is greater than 1. What about this one?
This will diverge.
That will diverge. The difference in degrees is only 1/2.
Is that your
I'm like,
fast point?
yeah, that's one of the two shortcuts.
Oh, nice.
I know, it is. It takes care of about half of them. Go
If
ahead.
the difference between it is less than 1, it diverges.
Less than or equal to 1, it will diverge. Always take denominator minus numerator. Make sure you take it in the right direction. Okay? All right, anybody else that on those? Yeah, go ahead.
What if there is no n, like say on the top? Can you still use this?
Yeah. What do you want down here?
N squared plus 7 plus 10 plus 5 minus 7.
Converge or diverge?
This would.
2 minus 0, is that what it is?
2 minus 0, that's exactly what it is. It's 2. Therefore, it will converge. Absolutely right.
Wait, what?
Pardon?
0?
2 minus 0.
Yeah, because there's
The
no
degree of this one is 0, n to the 0 power.
You take the greatest exponent.
Yeah, you always write this in descending order, so make sure the greatest exponent is first. All right, any questions on those?
No.
Ooh, this is pretty good, man. You guys, we may get out of here quicker than I thought. No, that's pushing it. That won't do it. That won't happen, but it's not going to be 8 o'clock. You ready? One more set of tests. Here we go. Okay, and these are alternating series. Alternating series.
You're on the page. Thank you.
All right, you're welcome. Okay, alternating series.
Remember not to close the mic. No, I just because I was listening to one of the YouTube videos that Tally was doing.
Alternating series. Alternating series are series of this form. They could either start this way or this way.
Is that T?
What is that?
What is that? What?
Is it -1?
It's a -1.
Oh, I'm not seeing it.
What the heck? Where else could it
Any
be?
kind of thing.
What?
Got a foreign symbol.
What the heck are you guys talking about?
It's like a euro symbol.
You should not attach the parentheses to the negative. People will misthink.
Oh, I see. You're thinking this is like
T, yeah.
a
Kind of
town.
Greek symbol.
Hey, I am part Greek, so
Epsilon.
there you go. Epsilon, yeah, there you go. Okay, these are alternating series. Example of an alternating series?
It jumps back and forth, positive to negative.
You bet it does. This is called the alternating harmonic. Okay, an alternating harmonic.
Diverges.
It's going to converge. But here we go. There's an alternating series test. Let's do it. Given alternating series. It's either one of those two. Well, I'll have to write them both. Sometimes they'll start with a +1, sometimes they'll start with a negative, positive, negative, but they alternate, okay? Given an alternating series, either one, doesn't really matter, okay? Then, if the limit as n goes to infinity of the a sub n is equal to 0, okay, and the terms are decreasing, so a sub n plus 1, okay, is less than or equal to a sub n, okay, then the series converges. Okay? Doesn't take much for an alternating series to converge. All you need to know is that the nth term is going to go to 0, and the terms, the a sub n parts, those positive terms, are decreasing, at least not increasing. You don't even have to know they're decreasing. At least they're not increasing. So, does the alternating harmonic satisfy both conditions? Well, let's see. The a sub n term here in the alternating harmonic is 1 over n. What's that limit as n goes to infinity of the 1 over n? That's equal to 0. That's the first condition. That's satisfied. And what about the terms themselves? Is it true that the terms are decreasing? In other words, that term is greater than or equal to the next term, which is greater than or equal to the next term, which is greater than or equal to the next term, oops, etc. And the terms are indeed decreasing. Okay? Given that the second condition is met, that alternating series converges. Okay? It converges. But there's a problem here. Okay, check it out.
Can you give us an example?
Another example?
Another one, yes.
Yeah, sure. Okay. Let's do this one. Let's go ahead and plus 1. And let's go 2 to the n.
So 2 to the n is the an.
Yes.
So that would be, what are we looking for? Sorry.
What is it? Here's what we're doing. We need two conditions here to be met. First of all, the a sub n. What's the limit as n goes to infinity of the a 2 to the n?
It's infinity.
It's infinity. It's not 0. Therefore, diverges and you're done. First condition is not met, you're done.
Okay.
Let's do another. Let's make it How about, how about something like this? Oh, how about, let's get a sign in there, what the heck? Well, we might as well do some, I think they're going to give you sines and cosines involved in there. Let's take a look at this one, okay? Let's generate a few terms to see what's going on. When n is 1, we get 1 plus 1 is 2, negative 1 squared is 1. You get the sine of pi. The sine of pi is 0. Okay, with me? Plus. Now when n is 2, I get 2 plus 1 is 3, negative 1 cubed, that's a negative 1. And it's 2, I get a sine of 2 pi. What's the sine of 2 pi? 0. And then I'm going to get a positive 1, and I'm going to have the sine of 3 pi. What's that going to be?
0.
0.
No.
Wow. Yeah, 0. What can you tell me about this series? Does it converge or diverge?
I thought we did sine and it diverged because it kept going, it keeps going on the x-axis or something like that.
Well, I have n times pi, so what I did by doing that is had each term equal 0. Because of the way sine is. At every pi of those values, it's equal to 0. Does this series converge or diverge?
Convergent.
It converges. Okay? Not only does it converge, we know the sum. The sum of that series is 0. Okay? So that one converges. Now, let me do a more complicated one. That one's too simple here. Let's do this one. It's probably what I should have done anyways. Let's do the sine of n pi over 2. This makes a huge difference. All right, now let's see what happens. When n is equal to 1, I get n plus 1 is 2. Negative 1 squared is 1. I get the sine of pi over 2. What's the sine of pi over 2? What's that?
It wouldn't be 0. Oh, it's sine. Oh, it's pi over 2.
Sine of pi over 2 is 1. So I get 1. Now let's let n equal 2. 2 plus 1 is 3. This is negative 1 now. Now, n is 2. I get 2 times pi over 2. The 2's cancel. I get the sine of pi with 0. And I get a plus. Now, n is 3. Okay, that will give me the plus here. 3 plus 1 is 4. But what's 3 pi over 2? Negative 1. Okay? With me?
What happens to the 4
What 4?
from the beginning?
Well, 4.
What 4?
The negative 1.
To the n plus 1. Oh.
Okay, and that's where you get the sign.
Yeah, that's n plus 1. Yeah. Okay. All right, then I'm going to get plus a 0, and then I'm going to get plus a 1 again, and then plus a negative 1. What about this series? Does it converge or diverge?
It diverges.
It diverges, because the limit is not equal to 0 here. There is no limit to these terms. You got 1, 0, negative 1, 0. See, this is what you were talking about before. There's no limit here when something does something like this. It's not approaching any one specific value. All right. What did I want to do? Oh, yeah. Okay. So to prove a converging, an alternating series converges or not is pretty simple. You look at the nth term, a sub n. Is it going to 0? Okay. If it's not, diverges. If it does go to 0, are the terms then decreasing? If they are, it converges. If they're not, it diverges. That's pretty simple, but that's not what you're going to be asked. Okay? You're going to be asked this. Given alternating series, either one, either starts with negative 1 or positive 1 and then alternates, okay? The a sub i's are all positive. Then, if, you got 3 possibilities here. Here are the 3 possibilities. If the positive series converges, in other words, forget the negative 1 part. If the positive series converges, the alternating series is said to converge absolutely. Converges absolutely.
What do you mean by absolutely?
Absolutely mean it converge. We don't need it to alternate to converge. The positive series converge. It doesn't have to go plus minus plus minus plus minus in order to converge. The positive series converges anyways. So the alternating series is said to converge absolutely. It's one situation. Second situation. If the positive series diverges and the alternating series converges, then the alternating series is said to converges conditionally.
So it's not a one times, it's just another one.
What's that?
For if, next to the if.
If, that's a 1. If that happens, then it converges absolutely. If this happens, number 2 happens, then it converges conditionally. And if number 3 happens,
What does it mean converges conditionally? I'm not getting that.
converges conditionally means the positive series diverged, okay, but the alternating series converged. We have an example of conditional convergence already. What do we have for an example of conditional convergence right now? We haven't done that many examples, but here's what we know. If we take the alternating harmonic, its positive series, the harmonic series, diverged. P series P equal 1. But the alternating harmonic converged. It met the alternating series test. Therefore, the alternating harmonic converges conditionally. Okay? I can see I'm losing people. So I got All right, I'm going to give you some more examples, okay? I think I lost 3. Third case. Okay?
So, in other words,
Go ahead.
the alternating series, you would have to technically find out if it diverges or converges. So there's really no, when you say conditionally, that means, in other words, it might or it might not.
No, it doesn't mean that. Conditionally means the alternating series does converge, but its positive series diverges. The only reason that alternating series is converging is because it does alternate. If it didn't alternate, it would diverge. But because it alternates, it's going to converge. That means it converges conditionally. And the alternating harmonic is an example of that. Because its positive series, the harmonic series, diverges. But the alternating harmonic converges. Why does it converge? As long as it goes plus minus, it will converge. Converges conditionally.
Okay, so it converges.
Yes, it does. But here's what you're going to be asked. I am going to give you 3 alternating series on your test. 3. And you're going to have to tell me the third one first. Let me do the third one. Third. Okay? Third one is what? There's only one left, and that is if the alternating series diverges, it diverges. Well, if alternating series, I'm really losing it here. Yeah, I know. You're right. If alternating series diverges, then you're done, and the series diverges. I worded that well, huh? Here we go. I'm sorry. All right. If it diverges, it diverges. You got 3 possibilities for every alternating series. Converges absolutely because its positive series converged. It converges conditionally because its positive series diverged, but the alternating series, converged. And 3, the alternating series diverges. Those are the 3 possibilities.
So why wouldn't 3 be like 1?
1 is just the opposite of 3 because if the positive series converges, the alternating series will converge, and it will converge absolutely. It doesn't even have to alternate to converge. All right, let's do some examples. You ready? How about this one? let's keep it simple. Okay, now, we know it converges, but does it converge conditionally? Does it converge absolutely, conditionally, or diverges? It converges absolutely. Why? What do? When you have to examine a series like this, the first thing you should do is look at its positive series. There's its positive series. What do we know about this positive series? What does it do? It converges. It's a p series where p is equal to 2. Since its positive series converges, the alternating series converges absolutely. Okay? Converges absolutely. Doesn't even have to alternate to converge. The positive series converged. Okay? Now, let's take a look at another one. Let's take a look at this one. First thing to do is look at its positive series. What can you tell me about its positive series? It diverges. Yes. It diverges. It's a p series, and p is only 1/2. Not good enough. Now, are we done? No, we're not done. All we've done is rule out absolute convergence. We've ruled that out. That's not a consideration anymore. We were down to 2 possibilities here. The 2 possibilities are it converges conditionally or it diverges. Those are our 2 possibilities. And how you determine which of those 2? Use an alternating series test on this. So I'm going to use the alternating series test on this alternating series. If it passes the alternating series test, this alternating series will converge conditionally. If it fails the alternating series test, it will diverge. Okay? So, alternating series test says to do 2 things. First, take the limit as n goes to infinity of 1 over the square root of n. What's that limit?
Wait, are you using the...
Alternating series test.
Well, what one are you using? Are you supposed to use
which one are you
regular
using?
the first one, negative?
What? Wait. Where are you guys now?
I thought, why would you use the positive version of it?
You have. That's what you do. That's what the alternating series test said. Here, let's go back. It's nice to have it. See, this is, just go back and say, okay, let's take a look. Alternating series test. Given the alternating series, this is this. Then what? Here's the alternating series test. You take the a sub n, that positive term, and see if it's going to 0. That's what I'm doing right now. And then I'm going to have to check and see if the terms are decreasing.
So if it goes to 0, then it would be divergent.
No.
No.
If this is going to 0 and this condition is met, if these 2 conditions are met, the alternating series converges. And consequently will converge conditionally. Okay? So, what's this limit as n goes to infinity?
Okay, converges to 0.
This 0, that's right. First part of the alternating series test is met. Okay, is everybody with me?
Louis,
Yes.
Some of us are.
let's keep going.
Adrian. Then I'm going on. All right, next. Let's look at these terms. The first term is 1 over the square root of 1, which is 1 over square root of 1. How is that related to 1 over the square root of 2? This one is greater than that one, and this one is greater than the next one, and that one's greater than or equal to the next one. In other words, these terms are decreasing. As I increase the denominator, I decrease the terms. Okay? And that keeps on going. That's the second condition of the alternating series test. Those terms are decreasing. This term is less than or equal to this term is less than or equal to this term, etc. The terms are decreasing. Okay? Therefore, the alternating series converges by the alternating series test. Therefore, this alternating series converges conditionally.
Now, if it wasn't like that, if it diverged, then
Okay, let's do it. Let's do another one.
it diverged.
Yeah, sure.
Wait, can you go back to
Whoa!
that?
What do you want me to do?
Why did the positive version diverge then?
Because that was a positive series. That was a p series where p is 1/2.
Yeah, but then it's the same thing. It's divergent. You guys said it converged.
Say that again now?
The second part, the limit, I don't get how that's converging.
Because in an alternating series test, all you need are these two conditions to be met for the alternating series to converge. See, the thing is, the rules are much simpler much easier for an alternating series. Since the alternating series is going plus, minus, the minus terms are subtracting from the plus terms. They're going to go to 0 a lot faster than just a positive series. For this positive series, it diverges. These are not going to go to 0 fast enough. It diverges. But these terms, as long as these two conditions are met, will go to 0 fast enough to cause the series to converge.
What's the second one?
The second part of it is that the terms are decreasing.
Oh.
You got 1 over the square root of 1, which is 1, 1 over the square root of 2, 1 over the square root of 3. Clearly, the denominators are increasing and the fractions are decreasing. That's all you need to have. These two conditions are sufficient for the alternating series to converge. Okay. All right, let's do another one. You ready? Here we go. Whoa, I got stuff underneath here. What the heck? All right, hold on a second. Oh, now the notes are all out of order and everything. Oh, no. Who's missing? Anybody missing? Raise your hand if you're missing. No? Oh. All right, let's try this one. Okay, let us do this one right there. Let's do this one. You tell me. What do we have in this alternating series?
AN will equal 1, right?
Yeah, that's true. That is true. Very nice. That is very true. So, what about this series?
It goes to 1.
You got 3 choices. And this is what I'm going to give you on the test. I'm going to give you 3 choices. A, converges absolutely. B, converges conditionally. C, diverges.
This one diverges.
That is correct.
Because there's no 0.
That is correct. This A sub n is not going to 0 as n goes to infinity. And as long as that's not going to go to 0, forget it. The series will diverge. Okay? Nothing more to do.
But don't you have to look at the A plus the alternate series after that? By
No.
the second rule?
You know what? That nth term divergence test that I gave you right off the bat works all the time for every series. If these terms, and what are these terms? These terms are going to be 1, -1, 1, -1, 1, -1. These are the terms of this series. Yeah, that's what these are. Because the nth term is not going to go to 0. If that nth term doesn't go to 0, I don't care what kind of series it has, it is. If the nth term doesn't go to 0, that series will diverge. This series diverges, okay? And there's nothing more to do. Now, you can go through the test, look at its positive series. The positive series would be an infinite set of 1s. That clearly diverges. Then what do? You look at the alternating series test. Well, the alternating series test fails. Why? Because the first part of the alternating series test is that the nth term must be going to 0. It's not. As soon as it's not going to 0, it fails. That series diverges, and that's what you have. Yes?
Are you going to do the third rule?
The what?
The third one.
That is the third one.
Oh, that is the third rule.
Yeah, we have, I gave you an alternate, I gave you a converges absolutely one, a converges conditionally one, and this one here diverges.
But the conditional one had the A to the N diverges well in the beginning.
Yes, here, let me give you another.
I'm sorry, I think I'm a little-
No, I should give you another one. We got plenty of time. Here we go. One more. You guys do this one. I've given you everything there is practically here. Let's do.
Diverge.
All right, I'm going to do this one. Yeah, that diverges. That's too easy. All right, how about this one then?
Too easy, that was hard.
No, that's too easy.
Wicked hot.
Why did you go to 0? I'm confused.
Wait, this one you're confused on?
Yeah.
Because this nth term here is not going to 0 because it's not. It diverges. That's it. As long as this nth term is not going to go to 0, it diverges. And as long as you have just an n up here and nothing down below, that's going to diverges. Okay? You with me on that? Is everybody okay? I know Danielle's with me. I know that, but anybody else with me? All right. I'm going to do another one. Let's do one more. Let's do this one. What about this one? Diverges is correct, because that nth term is not going to go to 0. All right, it's going to go to 1, and as long as it's not going to 0, that's going to diverge. Okay? That's it. It's going to diverge. Do you see this or not? You see it?
Because it doesn't, don't the.
Say that again now.
I thought the denominator was the positive series.
This is the positive series right here. Anything outside of the negative one. That's the positive series. And if you look at the positive series first,
That's going to infinity.
yeah, that's going to go to 1, not going to 0. The positive series diverges. So we've eliminated absolute convergence. Now you go to the alternating series test. Where's this term going as n goes to infinity? Is this term going to go to 0? No. This term goes to 1, not 0. Therefore, diverges. Done. Bless you. Yes. Bless you.
Does that say that diverges, right?
This one diverges. This one diverges. This one diverges.
I thought.
We're going to do one more.
You did n minus, you did 1 minus 1 equals 0, right?
So diverges because of that, right?
Yeah, there you go. That diverges because of that right there. How about this one?
The one with like conditional.
You want a conditional one? Okay.
It's conditional.
Here we go.
Yeah, now we know.
Just to see what that looks like.
Okay.
One, so that diverges.
The positive series diverges.
Yes. And then the other one.
Is the positive series, oh wait.
And then the other one,
1/2.
Why doesn't it?
I thought it would diverge too, no?
1/2, 1/5, 1/9, so it goes down.
I don't.
Well, it's not 1 over those things. It's n over those things. But it's still going to decrease.
Oh, you just put it in.
Here you go. You ready?
Just plug it in.
That was pretty good. That was pretty good. All right.
That was pretty good.
Here's what you do on this. First of all, you look at this and you say, oh yeah, this is going to 0, so I don't have an automatic diverging series here. Let's look at the positive series first to see if it's absolutely convergent. Here's the positive series. And in the positive series, you know this diverges because the difference in degrees is only 1, not good enough to cause it to converge, so this one diverges. Its positive series diverges. We've ruled out converges absolutely. That is ruled out. Now, let's go to the alternating series test to see if it converges conditionally or diverges. Those are the last two conditions. So, first thing to do is take the limit as n goes to infinity of n over n squared plus 1. What is that limit equal to?
0.
0. It is equal to 0. That degree is greater than that degree. That limit is equal to 0. Next thing to do, we have to look at the terms, and this is what Eric was just doing, looking at the terms to see if they're decreasing, okay? When it's 1, we get 1/2. And then when it's 2, we get 2/5. And when it's 3, we get 3/10. And then we get 4, we get 4/17. The numerator is increasing, but the denominator is increasing more, causing the terms to decrease. Now, here's one other thing I haven't mentioned yet. If you've got a series, and you want to know if it converges or diverges or not, it doesn't matter what happens to the first 10 terms, or first 100 terms, or the first billion terms. It doesn't matter. In other words, see what I've done here? These terms, that fortunately for us, they're decreasing right off the bat. But it's conceivable in the beginning they don't. But if after a while they then all decrease for greater than the 10th term or 100th term, that's good enough. Because it doesn't matter what happens to the first 100 terms, say, or the first any number of finite terms. It can do whatever it feels like doing. But if after that it satisfies the conditions, then we're done. okay?
So you start off with 100.
You can start off anywhere you want, but if you start off with 1 and it works, fine, you have it. But I'm just saying, it was possible that these terms actually jump up for the first one, and then they start decreasing. That's okay, as long as they continue decreasing after that. That's all that really matters.
Are we done?
Maybe we should do it more.
You can do it for homework. Do it for homework, then you can ask me. All right?